Okay, hi everyone. Now we will do some examples for the inverse Laplace. Okay, so first of all, what's the setting? Suppose you have a function f of s, f of z, with poles at s1 to sn, like in the picture here. Um, so here's a theorem to help us compute its inverse Laplace. Okay, so theorem. Computing inverse Laplace in terms of residue. There. Okay. So what's the deal? Um, so some conditions. First, um, set sigma, the one from Andrian's clip, the number sigma, to be so large that this number sigma is above the real part of any pole for all k 1 to n, where sk are the poles of f. Okay, good. Now the theorem splits into two cases. Case one, suppose that as the absolute value of y goes to infinity and x goes to minus infinity. So by xy I just mean this guys, right? So real part of z and imaginary part. So suppose that this go to infinity, um, suppose that when they go to infinity, you have the following limit going to 0. So f of z um, e. So if you take complex modulus, I'm writing here what you get in terms of x and y, and then f of x plus iy. Okay, suppose that this guy goes to 0. Okay, that's case 1. Good. Now case 2. Suppose that as y goes to infinity and now x goes to plus infinity, imply the same thing. So let me write it again. It says for completeness, ext x squared y squared f of x iy goes to 0. So this is case 2. Okay. All right. Good. Now in case 1, we have the following: the 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 function, because you do inverse Laplace, 2 pi I, right? Sigma minus I infinity, sigma I infinity, f of z, ei, sorry, zt dz. This guy, in case 1, will equal to the summation of the residues. Okay, so residue, um, yeah, so EZT f of z evaluated at sk. Okay, that's case 1. In case 2, so same stuff, but then it will be equal to 0. Okay, so that's the theorem. So case 1 could be true for some t. We will see that, right? So case 1 is 1 sec. So it depends on t, right? You see this t here. So if you like t1, t2, whatever t satisfy case 1, then we have this formula, and whatever t satisfy this, we have the second. So now let's do some examples. Proof, we have some notes, and we will upload it in the notes if you want to see the proof. Okay, but that, of course, we don't expect you to know that. It's only for it won't be tested or anything like that. Okay. Um, okay, example. So evaluate the inverse Laplace of 1 over s cube um, for right, real part s is positive. Okay, let's do this. So first of all, this is the function, right? So f of z is 1 over z cube. Let's check which case it satisfies. So let's check. So we had EZT, z, and times the function, right? Yeah. Okay, this is e to the xt, right? And then the z cancel out. So you have x squared, sorry, x plus I, but squared. All right, anyhow. Um, so now the question is, okay, what's the limit? Well, this is polynomial. So as x goes to minus infinity, this guy goes to 0. You don't even need to care about y, but let's just say it. But yeah, this goes to 0 because exponential, so this is negative number, right? Beats polynomial 1 over x squared. Okay, good. So we're in case 1. So case 1 for all t. This is true for all t, positive. We'll see that in some other cases, t changes the outcome. Okay, so what does that mean? It means that the Laplace inverse of 1 over s cube, we had this formula 2 pi I sigma. We just pick it to be, the pole is at 0, so we can pick sigma to be 1. So let me do it. And then uh, what is it? Z cube. Sorry. Yeah, so z cube and then e to the zt dz. Let me write z cube here. Okay, so yeah, this by residue theorem, we only have one pole at 0. So EZT z cube at 0, and the order is 3. So we have 3 minus 1 factorial, and then second derivative in z cube e to the zt z3 evaluate at z equals 0. Good. These guys cancel out, and you're just left with 1 over 2 e to the so t squared times e to the 0. So yeah, as expected, the answer is Laplace inverse of s cubed is equal to t squared over 2, like in the table. Okay, so that's how they find it in the table. Okay, now let's do another example where we have both cases. How are we doing with time? Okay, so let's do both. Yeah, it has both cases. So evaluate the Laplace inverse of this huge guy, e to the minus tz, or s, we can write either or, doesn't matter. So find this function where we take the real part of z to be bigger than 3 because of this factor on the bottom. All right, good. So let's check. Um, so first of all, yeah, the function is so the function is this. This is f. So let's check the which case it satisfies. Okay, that's the question. So as usual, we have e to the zt, z, and then we put our function. So z minus 1, z minus 3, e to the minus 2z modulus. Okay, so let's open this up. So this is ext. This guy is x squared plus y squared. This guy is e to the minus 2x. Uh, and this guy is, well, let me keep them like this. They don't really matter. So x plus iy, x plus iy. Because they're just polynomials, they won't matter. All right, so let's see what's going on here. Um, so we have e to the x t minus 2, and then we have a polynomial in x and y. Okay, so clearly the dominant behavior comes uh, from this guy. So we see that when t is bigger than 2, right, then x, then t minus 2 is positive, right? So, so as x goes to minus infinity, e to the x t minus 2 goes to 0. Okay, so so t bigger than 2 means case 1, and the reverse, t um, you know less than 2 means case 2, because as x goes to plus infinity, you get e to the x t minus 2 goes to 0. This guy now will be negative. So you need it, um, yeah, so it will be negative, so you need this guy to go to minus. So you need this guy to go to plus infinity. So let me write it. So you have x and then absolute value of t minus 2. All right, good. Now let's do some computations. Case 1, t2. Um, okay, so we want to find our function, right? So 1 over 2 pi I. The poles are 2 and 3, so let's pick 4. Even though it doesn't matter, you don't have to worry about sigma that much. You just have to make sure that all the poles are on the left. Okay, and then we have z t minus 2, z minus 1, z minus 3, dz. Good. So by by the theorem, let me just get straight to it. We have two poles, right? So one guy's here, another guy's here. So two poles, so two residues. Residue of f at, sorry, 1. I don't know why I said 2. 1, and then residue of f, sorry, capital F, at 3. Okay, and this is what we mean by capital F. Actually, let me write capital F because it will confuse you. Let me call it G. Okay, anyhow. Um, they're both order 1, so there's not much to do here. So we have z t minus 2, z minus 1, z minus 1, z minus 3, z minus 3. So I'm just computing the residues. These guys cancel out. These guys cancel out. Anyways, let me just write the final answer. So you get e to the t minus 2 with a minus and half, and e to the 3 t minus 2 with a half. Okay, so that's case when t is bigger than 2. Now when t is less than 2, we are in case 2. Okay, and we already said that, right? We said that f of t, I mean, I don't have to keep writing this, but it will be, that contour we wrote. You don't have to write this again, but let me just do it in a second. Um, this will equal 0. Okay, so you can just use the theorem. Okay, so all together, Laplace transform of e to the minus 2z, or let me say s minus 1, s minus 3, is a branch function. When t is bigger than 2, you have t minus 2 with a minus and 3t minus 2. But then when, 2. But then when t is less than 2, uh, what do you get? You get 0. Okay, so yeah. Do we have time for one more? It's fine. I think that's enough. Okay, so yeah, that's the main idea. So let's do one more. No, it's fine. It's fine. Okay.